Our planet's climate is driven by many forces, some well-known like ENSO, which stands for the El Niño Southern Oscillation, a climate pattern that describes the unusual warming of surface waters in the eastern tropical Pacific Ocean. This phenomenon is widely recognized for its significant impact on global weather patterns, causing everything from droughts to floods in various parts of the world. However, there are other forces, less famous but equally powerful, such as the Indian Ocean Dipole, IOD. The IOD is a complex climate phenomenon that involves the periodic warming and cooling of sea surface temperatures in the Indian Ocean, which can have profound effects on weather patterns across the globe. The IOD, a pattern of sea surface temperature changes in the Indian Ocean, can dramatically alter weather patterns, affecting continents far from its waters. This alteration can lead to significant changes in rainfall distribution, temperature variations, and even the intensity of monsoon seasons in regions like South Asia and East Africa. Understanding the IOD is crucial for long-range weather forecasting, helping predict seasonal conditions months in advance. Meteorologists and climate scientists use sophisticated computer models to analyze IOD patterns, allowing them to make more accurate predictions about future weather events, which is essential for planning and preparedness. This information is vital for farmers, emergency services, and water managers. For farmers, knowing the likely weather conditions can help them make informed decisions about planting and harvesting crops, potentially saving them from devastating losses. Emergency services can better prepare for extreme weather events, ensuring that communities are protected and resources are allocated efficiently. The IOD's influence extends from Africa to Australia, and as we approach 2025, signals from the Indian Ocean suggest a significant climate event. This event could bring about changes in weather patterns that might affect agriculture, water supply, and even the health of ecosystems in these regions. The Indian Ocean's unique geography allows for the development of distinct temperature patterns that define the IOD. The ocean's vast expanse and varied depths contribute to the formation of these temperature anomalies, which in turn influence atmospheric conditions and weather patterns. The dipole's two poles near Africa and Indonesia determine its phase: positive, negative, or neutral. In a positive IOD phase, the western Indian Ocean near Africa becomes warmer, while the eastern part near Indonesia cools. Conversely, a negative IOD phase sees the opposite pattern, with warmer waters near Indonesia and cooler waters near Africa. Each phase affects rainfall and temperature across vast areas. For instance, a positive IOD phase can lead to increased rainfall in East Africa, potentially causing floods, while parts of Australia may experience drier conditions, increasing the risk of droughts and bushfires. Today, October 1st, 2025, we are monitoring a transition into a negative IOD phase. This transition is being closely observed by scientists and meteorologists, as it could have significant implications for weather patterns in the coming months. This essay will explain a negative IOD and its implications for weather in Australia, Africa, and the maritime continent. A negative IOD phase typically brings wetter conditions to Australia, which can be beneficial for agriculture, but also increases the risk of flooding. We will explore the practical impacts on communities and industries. Industries such as agriculture, fishing, and tourism may need to adapt to changing conditions, while communities must prepare for potential disruptions to their daily lives. Finally, we will outline what scientists will be watching as this event unfolds over the coming seasons. They will be monitoring sea surface temperatures, atmospheric pressure changes, and rainfall patterns to better understand the IOD's impact and refine their predictive models for future events. The Indian Ocean Dipole, often abbreviated as IOD, is a fascinating and crucial climate phenomenon that acts like a seesaw of ocean temperatures across the Indian Ocean. Imagine the vast expanse of the Indian Ocean, stretching from the east coast of Africa to the islands of Indonesia, with its surface waters constantly shifting in temperature. The IOD describes how, at times, one side of this ocean can become significantly warmer than the other, while the opposite side cools down. This difference in sea surface temperatures can have far-reaching effects, influencing weather patterns not just locally, but across continents. When the IOD is active, you'll see warmer water accumulating on one side of the Indian Ocean, while cooler water dominates the other. This imbalance sets off a chain reaction, altering wind patterns, ocean currents, and even the distribution of rainfall. For example, a positive IOD phase brings warmer waters to the western Indian Ocean near Africa, while the eastern side near Indonesia becomes cooler. In contrast, a negative phase reverses this pattern. In a neutral phase, the temperature difference between the two sides is minimal. The ocean remains relatively balanced, and the IOD exerts little influence on global weather. During these times, rainfall and wind patterns tend to follow their usual seasonal cycles, without dramatic shifts. However, even small changes in sea surface temperatures can tip the balance, pushing the system into a positive or negative phase. These shifts can trigger significant climate events, such as droughts in Australia or heavy rains in East Africa, affecting millions of lives and ecosystems. To track the IOD, scientists use an index calculated from the temperature difference between two key regions: the Western Indian Ocean, near the Arabian Sea, and the Eastern Indian Ocean, off the coasts of Sumatra and Java. This index helps researchers quantify the strength and phase of the IOD, providing a valuable tool for climate prediction. Monitoring these ocean temperatures is a high-tech effort. Satellites orbiting above the Earth and buoys floating in the ocean constantly collect real-time data. This information is sent to scientists, who analyze it to forecast upcoming changes in the IOD and their potential impacts on weather around the world. The discovery of the Indian Ocean Dipole in the late 1990s was a breakthrough in climate science. Before this, many weather variations, especially those not explained by the El Niño Southern Oscillation, ENSO, remained a mystery. The identification of the IOD filled a crucial gap, helping scientists understand and predict complex climate interactions. Today, knowledge of the IOD has revolutionized long-range weather forecasting. Meteorologists can now provide more accurate predictions, helping farmers plan their crops, governments prepare for floods or droughts, and communities stay informed. For millions of people living around the Indian Ocean and beyond, understanding the IOD means being better prepared for whatever the climate may bring. The Indian Ocean Dipole, or IOD, is a powerful climate phenomenon that can dramatically alter weather patterns across vast regions. A negative IOD phase begins when the surface waters near Australia and Indonesia become unusually warm, creating a pool of heat that stretches across the eastern Indian Ocean. This warming is not just a subtle change. It's a significant shift that can be seen from space, as the ocean glows with higher temperatures. At the same time, the waters near the coast of East Africa cool down, forming a stark contrast between the two sides of the ocean. This cooling is just as important as the warming in the east, setting the stage for a dramatic shift in the balance of the Indian Ocean's climate system. The result is a strong temperature gradient stretching from west to east. This difference in temperature acts like a giant engine, driving changes in the atmosphere above and pushing tropical weather activity further east than usual. The entire system becomes unbalanced, and the effects ripple outwards. Over the warm waters near Australia and Indonesia, the heat fuels rapid evaporation. Moisture rises from the ocean's surface, filling the air with water vapor. This extra moisture leads to the formation of thick clouds and, eventually, heavy rainfall. The skies darken, and storms become more frequent and intense in these regions. The atmospheric circulation pattern is transformed. Air begins to rise vigorously over the warm eastern waters, while in the west, over the cooler African coast, air sinks back down. This rising and sinking motion creates a loop that reinforces the weather changes. Winds that normally blow from west to east across the Indian Ocean start to weaken, and in some cases, even reverse direction. This shift in wind patterns helps to sustain the negative IOD event, locking the new weather patterns in place for weeks or even months. The result is a moisture superhighway, channeling rain-laden clouds towards Australia and Indonesia. Meanwhile, the African coast is left high and dry, with much less rainfall than usual. This imbalance can have serious consequences for agriculture, water supplies, and even the health of entire ecosystems. In essence, the IOD acts like a giant switch, turning rainfall on for some regions while shutting it off for others. This dramatic shift in the balance of the Indian Ocean's climate can bring both relief and hardship, depending on which side of the ocean you call home. As of October 1st, 2025, climate models predict a strengthening negative IOD event. The IOD index has crossed the threshold for a negative phase, expected to persist through spring and early summer. These forecasts are based on sophisticated simulations processing vast data, giving us confidence in this prediction. The event is expected to peak in October and November, crucial for agriculture in Australia and Africa. A strong negative IOD means higher rainfall in some areas and lower in others, increasing the risk of extreme weather events. For Eastern Australia, a negative IOD typically means rain, as weather systems tap into abundant moisture. This increases the chance of a wetter-than-average spring, benefiting agriculture, but also raising flood risks. A wet spring can replenish soil moisture and water supplies, but also saturate the ground, increasing flood risks. Emergency services must be on high alert for potential flooding. The increased cloud cover leads to cooler days and warmer nights, reducing frost risk but heightening rain and flood risks. In southern and eastern Africa, a negative IOD points to drier conditions, with less evaporation and moisture. This can delay or weaken the short rain season, impacting agriculture and water availability. A failed rainy season can lead to crop failures and food shortages, affecting millions. Reduced rainfall also impacts water resources, hydroelectric power, and increases wildfire risks. The timing of the IOD's impact is crucial, affecting food security and water supplies well into the following year. The maritime continent, including Indonesia and the Philippines, experiences intense rainfall during a negative IOD. Warm sea temperatures fuel evaporation, leading to heavy rainfall and flooding. Major cities like Jakarta face heightened flood risks, with landslides and transportation disruptions. The economic and human costs can be severe, with agricultural activities disrupted and increased disease risks. The IOD's influence is deeply felt, affecting farmers, city dwellers, and the environment. Accurate forecasts allow strategic decisions, such as crop choices and resource allocation. The environment is shaped by the IOD, with increased rainfall leading to vegetation growth, but also higher bushfire risks. Understanding the IOD is crucial for global climate variability, with potential changes in its behavior due to climate change. As the negative IOD event unfolds, scientists monitor its evolution with real-time observations and model forecasts. Satellites and ocean buoys provide data on sea temperatures and subsurface conditions. Constant vigilance is essential for providing timely updates to governments and the public. The 2025 negative IOD event highlights the interconnectedness of our climate system and the value of climate science in preparing for large-scale shifts.